Good morning. This is the sort of the feedback from the physics lesson for Thursday, the 14th of January 2021. I just wanted to first of all just start by just pointing out that I'm recording this session, and also just to make you aware that it will be posted up on Facebook. So not Facebook, YouTube, so that you're aware that that it will be. Obviously, my advice is to keep your camera switched off. But however, if you do want to unmute yourself to ask any questions, please do as I go along. So we started with question 1 here, which is a past UFB question on momentum. It usually starts off easy and then ends up quite difficult. So this is all about a space traveler stranded out of space. They can't get back to their spaceship. They decide to rescue themselves by throwing an empty oxygen tank in the opposite direction to their spaceship. Explain using conservation of momentum, not using Newton's laws, but using conservation of momentum, why the plan might work. So the idea is that if you've got the space traveler and you've got the spaceship, okay, they throw their oxygen tank, they throw their oxygen tank that way, then that will then propel them that way because they'll have equal and opposite momentum. So we need to put that into words. So the idea is that they transfer momentum to the oxygen tank. So I would say that if they transfer momentum to the tank, because it's obviously an oxygen tank. If they transfer momentum to the tank, then they will have equal and opposite momentum to conserve momentum. To conserve the other idea, the total momentum is equal to 0. Okay, that's maybe how I would formulate an answer, although if I was an exam, I'd probably write a little bit more neatly than that. I do apologise. So that's the first answer. Basically, the idea is if there's a mention of conserving momentum, I would give a mark for that. And then the idea, then the recognition that they're going to move off in the opposite direction. If they throw the tank to the left, they'll move off to the right, or something to that effect. The next question says calculate the momentum. There, you've got to do some calculations. Now, in the mechanics paper, you will find that there'll be tables of data, and you have to be able to identify data from a table. So in order to do this, the traveller does some calculations based on the values shown in table 2. So you've got the mass of the traveller, the fastest speed they reckon they can throw the tank. That's an estimate. The mass of the empty oxygen tank, because that's obviously not going to throw a full one, and how far they've got to go to the spaceship. We're going to assume that everything is stationary before they do this. It doesn't say it in the question, but really, unless you assume everything's stationary, then you really can't do the calculations very well. So the first one says calculate the momentum of the empty oxygen tank, include the correct units. Well, I think this is going to be the momentum after it's been thrown. So this is going to be 30 meters per second is the speed, and the mass is 10 kilograms. So the momentum is mass times velocity. This isn't a very clearly written question, to be honest. So this is then 300. Now it says include the correct units. So it's kilograms, meters per second. Okay. So if that's the case, well, you would get 1 mark for 300 for the correct answer, 1 mark for the units, even if the answer was wrong, because one of the marks is to actually include the correct units. It then says hence. Now, hence is an important word in exams. It means using the previous information. It says state the momentum of the traveller after they've thrown the tank. Now, if it also then says state, it usually means that that answer is there somewhere already, or it's a simple statement. It doesn't require a calculation. Well, if they've thrown the tank, if that's the momentum gained by the tank, then there'll be an equal and opposite momentum. Now, in this, it would be acceptable to give that answer, but really and truly, I would put a negative there. I think for a 1 mark question, it's unlikely that there will be that the sign will matter, but I think it's best to put it in because it's correct, isn't it? Because they have to gain an equal and opposite momentum. Momentum before, if everyone's stationary, is 0, so momentum afterwards has to be 300 minus 300 to make 0. It then says, hence show the speed of the speed of the traveller after the thrown tank is approximately 2 meters per second. So if that's their momentum, you know that momentum, which is 300, now it says speed, so I'm going to ignore the sign because it's a scalar. That's the momentum, magnitude of the momentum, and it's mass times velocity. So the mass of the traveller in the spacesuit is up here, 150 kilograms. So I'd say that's 150 multiplied by the speed. So the speed is 300 divided by 150, which is equal to 2 meters per second. Okay. What I'd be looking for if I was marking that as an examiner, I think what I'd really be looking for is either that or both. But that would be the key bit, the idea that you're using the formula for momentum to calculate the speed. It then says, for part B, the traveller then travels towards a spaceship and eventually reaches it. Calculate the time taken to reach the spaceship. Well, after they've thrown the option cylinder, they're going to move with a constant velocity, a constant speed. And it tells you it's 2 meters per second. So even if you couldn't do that bit, you're given that information. So the speed is 2 meters per second. What else do you need? Well, if they're traveling at constant velocity, you're going to need the distance. So S is the distance, which it tells you in the table is 1 kilometer. So that's 1,000 meters. So the time, well, if speed is distance over time, then time is going to be the distance over the speed, which is going to be 1,000 over 2, which is 500 seconds. Okay, and all I'm really after, the bit that I'll be after if I was marking it, would be the 500. Okay, so the next part says, upon reaching the spaceship, the traveller slows down to a stop by reaching out to the spaceship and pushing with their arm. They travel a distance of 1 meter while they're doing so. Calculate the deceleration of the traveller. So here we're actually going to use the Suvat equation that we did before Christmas. So here we're going to use the Suvat equation. We've got the distance. We want to work out the acceleration because we want to work out the deceleration. That's what we want to work out. We don't have the time. Okay. We do have the initial velocity. We know that it comes to rest. So that's 0, the final velocity. And we have the distance. It's 1 meter. So what we're going to use is v squared equals u squared plus 2as. Okay, so that gives you, that'll give you the deceleration. Well, the deceleration or the acceleration is going to be v squared minus u squared over 2s. Substituting our numbers, well, the velocity was 2 meters per second. So they're going to start off, they're going to end up at 0 because it comes to rest, minus 2 squared equals 2 times 1, which comes out to be minus 2, okay? Meters per second squared. So the deceleration is a negative acceleration. So I would actually then say it's 2 meters per second squared. But you know what? If you just quoted that as your final answer, you'd probably still get the mark because really, what I'm looking for as an examiner is I'm looking for the fact that you were able to recognize that this was going to be the required equation, the use of the equation to get something, to get a correct answer. So the rest of it, I don't think is particularly a problem. Okay, so that minus sign, sorry, I don't think it's a particular problem. But to be absolutely correct, really you want to be getting rid of it because you're calculating a deceleration, which is a negative acceleration. You then calculate the force applied by the traveller in making themselves stop. Now, there are a couple of different ways of doing it. Probably the easiest way is to use F equals ma, Newton's second law of motion. Okay. So the mass of the traveller in the table, it was 150 kilograms, multiplied by the deceleration, which is 2, makes 300 newtons. Okay. So that's your answer. It's using F, 1 mark for using F equals ma, 1 mark for the correct answer. Okay. You can do it as a rate of change of momentum if you like, but you don't have the value for time, so it would be quite difficult to do. That's probably the easiest way to use Newton's second law of motion. It then says state whether the traveller would be able to provide this force, well, suggest. So it's not really the yes or the no, it's the justification. Well, in my opinion, I think they probably would just about be able to do it, okay? The reason why they'd just be able to do it is it's a similar force to lifting a 30 kilogram bag. So if you think about it, or 30 kilogram mass, if you think about it, if you've traveled by air recently, your suitcase will be about 20 to 30 kilos, depends upon how much luggage you've paid for. And well, it kind of works, doesn't it? Yeah, then you can just about lift it. So yeah, should be all right. So the next part is then to say that the traveller is now safely in the spacecraft. They turn the rocket engines on. Exhaust gases leave the back of the spacecraft at a speed of 1,200 meters per second. This propels the spacecraft forwards. Okay. Now, it says state the formula linking force, change in momentum, and time. So this is Newton's second law of motion in terms of momentum. So force is the change in momentum over time. That'll do nicely. That's it. Easy as that. This next one is really difficult. The reason why is because in all the foundation exams, there'll always be a couple of questions which are just extra difficult. Okay, that's really because we need to make sure we justify an award of a distinction grade. So this is a 3-mark question, and it's a proof, and it's proving a formula that you've never seen before. Okay. So I'm going to show you how you do this. This requires a little bit of thinking. So if we show that the force from the engine is given by this formula, where rho is the density, A is the cross-sectional area of the rocket nozzle, and V is the speed of the exhaust gas. Well, if we think about it, if you've got a rocket nozzle, there's your rocket nozzle, there. It's going to fire gas out at a particular rate of 1,200 meters per second. Now, if we think about it, the gas is going to come out sort of like a big cylinder. And after a certain length of time, that gas will have moved from here to here. So it will travel the distance d. Okay. Now, we've got here, the factor that's here is the cross-sectional area of the rocket nozzle, which is there, A. Okay. Reason why we've got that? Well, we've got a few clues here. Got something to do with density. It's probably, as this is a section 1 and section 2, it's probably got something to do with that. So let's start with that. Force equals the change in momentum, delta mv, over t. Okay? That is just that formula written in symbols. So if we think about it, if we've got here density, and here we've got a mass. Now, as a formula that links density and mass, we've got the idea that the mass is density multiplied by the volume. Well, the volume of what? Well, here we go. We're pushing a cylinder of gas out. We've got an area and a distance it's moved. It's going to be the volume of that cylinder. So that's going to be rho A times D. Okay, so we can substitute that in. So it's a change in rho A D, because that gives the mass, multiplied by the velocity, divided by the time. Okay, now it's a change. So what's going to change? Is the density of the gas going to change? Not really. Is the cross-section area of the nozzle of the rocket nozzle going to change? No. Is the speed of the gas changing? No, it tells you it's constant, 1,200 meters per second. So the only thing that's going to change is D, because as the gas continues to be pushed out, this cylinder is going to get longer and longer and longer. And so, okay, as it pushes more gas out. So it's D, so it's the change in D. So it's a change in distance over time. Well, that's the speed. Okay, so it's rho A V times V, which is equal to rho, the density, times the area, times the speed squared. So as an examiner, what am I after? Well, what I'm after, first of all, is the easy bit, the identification of the fact that you're probably going to want to start with that formula. If you linked mass, density, and volume, that was another part. And then the third part was really just putting it together, recognizing that delta D over T was going to be the speed. Okay, so those are the three stages I'd be looking for if I was marking this as an exam. As I said, this is a distinction level question. This is designed to be very hard to do. So if you struggled with it, don't worry, it's designed that way. So let's now move on. So the second question for you to have had a go at is to look at the idea of a student jumping off a small boat. We're going to assume it's stationary at the beginning. So explain the principle of conservation of momentum, why the boat moves in the opposite direction to the student. Well, principle of conservation of momentum is that the momentum is conserved. So we can say the total momentum before equals 0. And that will be the total momentum before and after. So what we said there is it's conserved. We then want to really just link it now to the situation. So the student gains, let's say the student gains positive momentum. So the boat has negative momentum. To conserve momentum. Okay, and that's it. Easy as that. Then we've got another table of results. As I said before, the mechanics paper, there's lots of tables of values. So here it says state the momentum for the student and boat before the student jumps off. So state doesn't require any detail. Before the jump off, it's 0. State the total momentum of the student and the boat after the student jumps off. 0. How do we know? It says state, so it's an obvious, simple answer. Doesn't require much in the way of calculation. It then says calculate the momentum of the student after jumping off. So after they've jumped off, that's going to be mass times velocity. So the mass of the student is here, 80 kilograms, and the speed is 33 meters per second. So that's 80 times 3, which is 240 kilograms meters per second. Okay. It then says hence. Hence means using the previous answer, state. So it's going to be using the previous answer. It's something in the previous answer that we're going to state. Well, the momentum of the boat after the students jumped off, well, it's going to be negative, minus 240 kilograms meters per second. As it's a 1 mark question, we're probably not going to bother that much about the negative sign. So if you miss out the negative sign, it's probably going to be all right anyway. Right. It then says, hence show. So hence means using the previous answer again, show that the speed of the boat after the students jumped off is 12 meters per second. So what we've got to do is we've got to conserve momentum. Yeah, it's the speed, not the velocity, so we're going to ignore the sign. The momentum was 240, which is equal to mass times velocity. Now we want to work out the mass. Mass is here, 20 kilograms. Okay, so that's going to be 20 times the speed, v. So v is going to be 240 over 20, which is 12 meters per second, which is shown. Okay, again, 1 mark, not for that bit because that's already stated. It's really for this bit here. That's what you get the mark for, is using the formula. Okay, it then says later on the student walks into a lamppost. So they're very unfortunate. First of all, they fell out of a boat. Now they've walked into a lamppost. And it comes to rest from an original speed of 3 meters per second in 1 second. So first of all, we've got to calculate the change in momentum. Well, if they come to rest, the change in momentum, they end up with a momentum of 0. So they had the momentum before, which was 3 times their mass. The mass in the table was 80 kilograms. So 80 times 3 gives you 240 kilograms meters per second. Okay. So that's their change in momentum. It then says calculate the deceleration of the student. Now, probably using a change in velocity over time. So we know the acceleration is going to be change in velocity over time. So the change in velocity is 3 meters per second. The time is 0.1. That's going to be 30 meters per second squared. Okay. It then says calculate the force applied to the student to make them stop. So the force applied to the student to make them stop. There are 2 ways of doing this. You can use either one as long as you show you're working. So you can either use the rate of change of momentum. Okay, because we know the momentum was 240, so the change in momentum was 240 kilograms meters per second, divided by the time taken of 0.1, which is 2,400 newtons. That would be acceptable. You get both the marks, one for recognizing it's a rate of change of momentum and one for the answer. Or you could use Newton's second law of motion, the other second law of motion, F equals ma. So if the force is mass times acceleration, we know the mass is 80. We know the acceleration from the previous question is 30. So 80 times 30 still gives you 2,400 newtons, exactly the same answer. So either one of these will do nicely. 1 mark for the answer, 1 mark for showing the working. So if you just wrote 2,400, you'd only get 1 mark on this one. Last one, why suggest why people think lampposts should be wrapped in shock absorbing material. Well, what do we mean by that? Well, shock absorbing would be something that reduces the force. So the material, so like if it's padded, for example, then the lamppost should be then obviously there'd be fewer injuries. Okay, so how does that work? Well, we said before, the key is the increase in collision time. So what we want to do here is we want to say that padding would increase, make bigger collision time okay, reducing the force. Well, I'm going to be a little bit pedantic. I'm going to say for the same change in momentum. Okay, so that's the idea. The idea is we're increasing collision time. As this is 1 mark, that was the bit that I would look for as an examiner, the idea that you're increasing the collision time. Okay. Now, if you sometimes get exactly the same question, but worth 2 marks. So the 2 marks, you probably want to put a little bit of justification in it. So the idea is that it increased the collision time, thus reducing the force for the same change in momentum. So this bit would be the bit that would be really essential if this was a 2 mark question. However, as it's a 1 mark question, the only bit I'm really interested in is that bit there, increasing the collision time. Right, so those are the questions that I gave you as your sort of your final task of the week. Obviously, there's a Seneca task which I'll be looking at this afternoon and giving you some feedback on. What I'm also going to do is I'm going to talk you through your homework. Now, as we go through our homework, this is the actual weekend homework. It's a simple one, doesn't require any writing, but obviously it would make sense for you to spend some time going over the paper, going over the work that we've done this week. Make sure you understand it. And I think what I'd like you to do though is to watch these 2 videos. Just to introduce them, this video, the first video, is quite short. It's quite a short one, and it talks about elastic and inelastic collisions, which we'll look at next week. Seeing Through Science, again, takes you through in a bit more detail. It's a slightly longer video, but it's actually looking at an application of Newton's laws, which is actually quite fun to watch because it's all about fairground rides. So I'd like to watch both of these videos. The whole thing will probably take you about 35 to 45 minutes to watch them both if you just watch them once, but it will help you to gain a bit more context and a bit of enrichment to that subject. So with that in mind, I just want to wish you a good weekend, and next week we'll be looking at energy in motion, work, power and energy, and then we'll be pretty much finished and just going over the last few tasks. So have a good weekend.